Hello, cutie patootie, math angel. Welcome back. This is Decaf-Math ASMR. Today, let's take a look at some different types of matrix multiplication, and we'll also review the standard common way of multiplying matrices, just so that we can have these all in one place. But we're going to look at the Kronecker product, the Hadamard product, as well as Khatri-Rao. So feel free to play along with this if you want to, if you find it interesting. And you can also feel free to just sit back, zone out, relax, and maybe even fall asleep. If you find this boring or sleep-inducing, you won't get in trouble and I won't get mad. And if you want to come back, you always can. You can always come back and review the math later. So, this is going to be very, very casual. I'm going to take a look at a concrete example just so that we can focus on more of a how-to today, just a more algorithmic approach. And this way we can have concrete numbers to work with and just introduce these different types of products. So I haven't worked these out ahead of time, so hopefully we get the right answers. But the most important thing is to just celebrate this little moment of peace and quiet and a little bit of math. So there's absolutely no pressure, no added expectations or anything. I just want you to feel safe and comfy, and thank you for being here. Oh, and if you're wondering what this is, it is a little microfiber cloth. So on one side it is nice and fluffy. And it's soft. And then on the other side it has this more abrasive, scratchy texture. And I really like the sound. I thought you might too. So, does it make you want to clean? Or is that just me? What do you think? Do you like it? Let me get it closer. It's like this staticky type sound. I feel like I could make an entire video with just this. Anyway, I'm going to use it to erase the whiteboard as we go. Okay, so let's start by writing out the two matrices that we're going to work with. I'm going to just work with 2x2 cases. So each of these matrices are going to have 2 rows and 2 columns, just to keep the calculations more straightforward and just so that we can focus more on the patterns rather than get all bogged down with calculations, even though there will be a few here. So let's have matrix A and matrix B, and A is going to be 1, 2, 3, 4. I know, totally unoriginal, but sometimes simple is best. So then B is going to be, can you guess? 5, 6, 7, 8. So we have 2 rows and 2 columns. 2 rows, 2 columns. So these are each 2 by 2. And even though this is going to be the example that we're working with today, I don't mean to imply that all of these products require that the 2 matrices have the same dimensions as each other, nor is it necessarily necessary that each of the matrices are square, meaning that they have the same number of rows as columns. But as we look at what or how the products work, I think that will become clear. Okay, so this is just kind of the overlap of all of the different requirements, so we can actually find the product of these two for all of the cases here. So if we want to generalize the elements here, we can write these matrices as using our indices, so our row column notation. So for matrix A, we could write A11 to represent the element in the first row and first column. This would be the first row, second column, so A12, and then A second row, first column, so A21, and then A22, second row, second column. We can do the same thing for B. B21, B22. Okay, like so. So we can generalize the algorithm for how to actually multiply these using this instead of specific numbers. So in this case, A11 is 1, A12 is 2, A21 is 3, and A22 is 4, and the same thing for B. So first we're going to do the regular common product. So that's just going to be AB like that, squished together. This is generally how we write the standard common way of multiplying matrices. Even starting in algebra, we learned that there are a lot of different ways to write times. And then later on, we learned that dot and times, the cross product, actually can mean different things. So we just have to be careful how we write this. But AB like this is the common notation. And you might see stuff like this, or times with the circle around it, or this, or an asterisk. And these all mean different things. So I'm just going to use the notation that I'm comfortable with, but definitely, just be aware that there are different ways of writing this stuff, and you can adapt to whatever it is that you're learning. But usually when we squish A and B together like that, this is just standard multiplication. Let me write this in black actually. It's just standard multiplication, and let's go over how to actually carry that out. So if I have 1, 2, 3, 4 times 5, 6, 7, 8. What we do here is we work with rows of the first matrix A and columns of the second matrix B. And if we treat those rows and columns as vectors, then we basically dot those vectors together. But in general, all that means is I take this first row and this first column, and I multiply corresponding elements together. So 1 and 5 multiplied together, and 2 and 7 multiplied together, and then I add those products. So it's going to be 1 times 5 plus 2 times 7. And in general, using order of operations, multiplication comes first before addition. So I don't need these parentheses, but I'm going to put them there just to make sure that we're extra clear, okay? Then we go ahead and do the same thing for the next row and column. Rather, the same row, but the next column. So we're finding all the different pairs here. So we do 1 times 6 and 2 times 8. And again, we do the products first, and then we add. Okay, and then we move on to the next row and that first column again. So 3 times 5 plus 4 times 7. And then it's a matter of actually calculating out these products. And then we take 3, 4 and do the same thing with 6, 8. So 3 times 6 and 4 times 8 here. So, of course, if we have more terms here, we just keep going with the same pattern, okay? So, as far as we can tell here, there's a little bit of a requirement for the actual dimensions here. Because we're doing rows from A and columns from B, the pairs of the elements need to actually line up. So we couldn't have like 5, 7, and then like 9 here with nothing else here, because there would be no match. And we can't just throw in a 0 because that's a different matrix. So the requirement for dimensions for this standard common product is simply that the number of columns in matrix A has to equal the number of rows in matrix B. And because here we have 2 by 2 by 2 by 2 by 2 and 2 by 2, that happens to be satisfied. But in general, if we had, let's say, 2 by 3 and then 3 by 4, that's okay too, because when we go this way, the number of terms this way across is actually the number of columns, right? So I know we're moving this way, but to know how many numbers, that would be the columns, and going downwards, the number of terms going downwards here is actually the number of rows of B. So they need to line up. So in general, as long as we have something like M by N for A and then N by L for B, we would be good to go. So the second dimension of A has to equal the first dimension of B. Okay. So now let's just go ahead and calculate this. 1 times 5 is 5, 2 times 7 is 14, then I go ahead and add. 1 times 6 is 6, 2 times 8 is 16, and then I'll add those. 3 times 5 is 15, 4 times 7 is 28, and add. 3 times 6 is 18, 4 times 8 is 32, and add. It's a nice little dance. 5 and 14 is 19, 6 and 16 is 22, 15 plus 28 is 43, and 18 plus 32 is 50, right? Hopefully that's all good right there. But notice that we have a 2 row by 2 column for answer for this product. And in general, with M by N and then multiplied by an N by L, I think I said, the answer would be M by L. But 2 by 2 by 2 by 2 would just be 2 by 2. So it works out nicely like that. And from there, it's just a matter of practicing and making sure that you're writing the correct pairs in the right spot. But from there, it's just some basic calculations, okay? Okay, so just to say it out loud with our general terms, for the basic multiplication, we have A11 B11 plus A12 B21, then A11 B12 plus A12 B22, then A21 B11 plus A22 B21, and then A21 B12 plus A22 B22. So next up we have the Kronecker product, which I'm going to write with the times in a circle around it. The Kronecker product, which is just what you get when you multiply things together. And for the Kronecker product, we basically take each element of A, so 1, 2, 3, and 4, and we multiply it by the entire matrix B. So we're going to form this big matrix matrix here, and we take 1 and multiply it by 5, 6, 7, 8. And then we take 2 and multiply it by 5, 6, 7, 8. And this might be really satisfying to work with in general, but it's really cool to think about, just start thinking about different properties of this, right? So essentially, we're basically distributing out, kind of like distributing over B. So 5, 6, 7, 8. So the way that I have it here, it does look like, when you take a matrix and you multiply it by a scalar, you get a matrix. You basically just multiply each of the terms by that constant number. But here it looks like that, and it's true. We're going to distribute this 1 over it, or 2 and 4, whatever, 3 and 4. But this is not actually going to be like a matrix of a matrix. So we are going to just get rid of these brackets here and just keep the elements. This is just how I'm writing it. So this is 1B, 2B, 3B, 4B. So it's not like a nested matrices, okay? It's just going to be the elements. So basically, 1 times 5 is 5, 1 times 6 is 6, 1 times 7 is 7, and 8. 2 times 5 is 10, 2 times 6 is 12, 2 times 7 is 14, 2 times 8 is 16, and we just squish them together like this. Then we have 3 times 5 is 15, 3 times 6 is 18, 3 times 7 is 21, 3 times 8 is 24, 4 times 5 is 20, 4 times 6 is 24, 4 times 7 is 28, and 4 times 8 is 32. So we have a little bit of times tables practice here as well. But see, once we expand it all out, we have 4 rows, 4 columns. So the Kronecker product actually expands everything out. And the important thing is that we take all the elements of the first matrix and multiply it by the entire second matrix. So as you can see here, the actual number of elements or dimensions don't matter whatsoever, because even if this is enormous, we just take each element at a time and multiply it by this whole matrix B, and everything gets expanded out. So this can be m by n, this can be p by q, and then everything multiplies. So we end up getting like the rows multiply and the columns multiply. But in this case we have 2 by 2 and 2 by 2, so we get a 4 by 4. Okay, so that's our Kronecker product. Okay, very nice. So then next we have the Hadamard product. I guess if we wanted to write the general notation for this, it's going to be really large to say out loud, but it's A11, B11, A11, B12, and then if I'm going across, it's going to be A12, B11, A12, B12, and then down here and down here. So you just go ahead and write it all out, but it should be every pairing here. Okay, so then for the Hadamard product, I'm going to write it with an asterisk, but I've also seen it with like a circle like that. This is Hadamard. This is actually, I think, the most straightforward one. And we can just basically multiply this element-wise product. So basically, I multiply 1 and 5, 2 and 6, 3 and 7, 4 and 8. Very straightforward, yeah. So finding corresponding elements and multiplying them together. So naturally, in this case, the dimensions of A and B have to be equal. We have to actually have pairs, and again, we can't just throw in zeros where they don't exist. We literally just multiply the pairs and make sure that the dimensions are the same. Okay. And the funny thing about this is that usually when people first learn about matrix multiplication, the standard common one with the rows and the columns, it's actually tempting to just do this for the product, especially if the dimensions are the same. Because when you add and subtract matrices, like if I were to add and subtract these, you actually do add and subtract corresponding elements. So then if I said, hey, what do you think multiplication would look like? You might think to multiply corresponding elements, but that's actually not correct for the standard multiplication. You have to do the row and the column thing, but this product actually does exist. So if you happen to be learning about common multiplication for matrices and your teacher's like, no, that's not how you do it, you can just be like, actually I'm doing the Hadamard product. But don't tell anyone, and don't tell them that I said that. But this is not how to do the standard multiplication. This is just a different product in itself, okay? So just multiply corresponding elements. And again, dimensions have to be equal. So lastly, let's move on to Khatri-Rao. Last but not least, this one's really cool to take a look at. And I'm going to write this as a dot with a circle around it. B. Khatri-Rao. And so what we do here is this is actually also known as column-wise, the column-wise Kronecker product. So we're going to borrow that idea of distributing the entire second matrix, right? This is the one where we take each element of A and multiply it by the entire matrix B. So we're going to do that here again, but we're going to break A and B down into columns. So instead of looking at it as 1, 2, 3, 4, and 5, 6, 7, 8, I'm going to treat A as the column 1, 3, and 2, 4, and then B as 5, 7, and 6, 8. And we're going to treat those columns as individual matrices. And then what I'm going to do is take the Kronecker product between 1, 3, and 5, 7, and then 2, 4, and 6, 8. And then we just squish it all together. Okay, so what that means is 1, 3 is a matrix, 5, 7 is a matrix. And we just end there. So we take an element of A, so 1, and we multiply it by the entire first matrix, the first column. Then we take 3 and 5, 7, like that. And then we can do the same thing with the second columns. So 2 with 6, 8, and 4 with 6, 8. And again, this is not a matrix, not like nested matrices here. We're going to get rid of these brackets on the inside. We're just talking about the elements. So it's not a matrix of matrices. This is just how I'm writing it out. And you don't want to do, just make that clear for yourself. This way makes sense to me, but you don't want to do like a determinant to signs. So this kind of makes sense. But you have one big matrix and you do 1 times 5 is 5, 1 times 7 is 7, 3 times 3 is 9, 3 times, oops, I actually wrote that wrong, this is 5, right? So 3 times 5 is 15, 3 times 7 is 21. So you just go down like this. 2 times 6 is 12, 2 times 8 is 16, 4 times 6 is 24, 4 times 8 is 32. Ta-da! So we have 4 rows and 2 columns here. So that's it. And all we're basically doing is taking each column and doing the Kronecker product and then pushing them together. So we would still have the 2 columns in our answer, but we're basically expanding out just this bit here. So that's why we have 4, because we're multiplying the 2 by 2 parts. But instead of doing a 2 by 2, we have 2 2 by 1s basically in this particular case with our 2 by have 4 by 2 for our Khatri-Rao. So naturally, if we have more terms, this would expand out more too. Hope that makes sense. So basically, we treat this A1, 1, A2, 1 as a column and its own matrix. So you could do like A1, A2, A3, dot, dot, dot. And then same thing for the B, B1, B2, B3, dot, dot, dot. And then do the Kronecker products between each of these individual ones. A1 cross B1, A2 cross B2, A3 cross B3. So that's all for now. I hope that you're nice and relaxed, and I hope that you're enjoying this. Thanks for spending some time with me today or tonight. I'll see you around for more math very, very soon. And if you are asleep right now, I'm wishing you sweet, sweet mathy dreams.